Right, where we stopped last time is we were just discussing Charles's law, the influence of where we've got temperature and volume in the container that we're dealing with. Now we've got to go a little bit, and we spoke about the absolute zero concept as well before. The next one was, let's have a look. Remember, we've looked at pressure. We've looked at pressure and volume. We've looked at temperature and volume. Now we must look at temperature and pressure. And if you sit down and think in everyday life, every single one of these is perfectly obvious. We don't even have to think about it. It's blatantly obvious in everything that we do. So this is not a very difficult section of work. Very important section, because when we start with actually putting the chemicals together in stoichiometry and equilibrium chemistry, we're going to start looking at the gases and how they react with things. But let's have a look what happens if we do temperature and pressure now. There's a law, and it was Gay-Lussac, another French guy, who came up with this one. And it says, increasing the temperature of a gas increases pressure. The pressure is directly proportional to the temperature. Okay. How does that look if we do a little drawing of that as a graph, right? We say pressure and temperature. We say it's directly proportional. As we increase the pressure, the temperature goes up. And remember, all of these graphs we're doing are ideal graphs, not doing deviations from it. That we'll get into at a later stage. But that's obvious as well, isn't it? Think about it. A pressure cooker, right? You've all seen a pot on the stove with, say, water in it or anything you like. As it starts warming up, right, what are we doing? We're increasing the kinetic energy of the individual molecules in our pot of water or soup or whatever. They start to move faster. As they move faster, they get more energy. Therefore, what happens is eventually the velocity, okay, let's have a look at the surface of the water, shall we? Over here. Here's my individual molecule of H2O. It's now got enough energy to escape. It breaks through what's called the surface tension of the water, and it escapes into the atmosphere. All right? Each time that one or more of those are escaping, obviously the water level goes down, doesn't it? But now imagine if we had closed it. Those water molecules that have got that temperature have got nowhere to go. So they start, more and more of them start bouncing around inside the pressure cooker, the pot, right? And eventually it gets so much that the lid of the pot starts bouncing up and down. That's actually releasing the excess pressure. When the pressure upwards is bigger than the weight, that's Newton again, right? The pressure upwards of the gas is bigger than the weight of the lid. What happens? It lifts the lid up. And then the pressure drops because some of the gas can escape. All right? There's Newton involved in it as well, right? So this energy of these molecules have increased. Remember what we said is that every atom or molecule hitting on the side of the container like that was a measure of the pressure. Therefore, the more we had in, the more hits we got per second, therefore the more the pressure was, right? Well, same thing, we have increased the temperature, therefore given the molecules more energy, therefore we've increased the pressure, right? Very, very simple thing to actually think about, because it's something that we see on a daily basis, right? Okay. Now, let me just put this over here. So what have we got? We've got this situation here where we've got the pressure and volume and the temperatures related, right? Essentially what we're doing with this, all right, is we are doing this, okay? We are creating a situation where we end up with a law that says P1 V1 over T1 equals P2 V2 over T2. Okay? What is this saying? It's saying that if we know situation 1, let's call this state or situation 1. This is then state or situation 2. Okay? If we know pressure, volume, temperature, pressure and temperature there, we can work out volume. Correct? Or any. So we've got 1, 2, 3, 4, 5, 6. So if they give us 5, we can work out number 6 by just putting them into the equations. What are the rules that we follow? First thing, temperature is always in Kelvin. Secondly, pressure is always in Pascal, which is newtons per square meter. Be very careful here, because very often the pressure is given as 25 or 2.5 times 10 to the 4 Pascal. Remember? Okay, we're working in that there, so it's not 2.5, it's 2.5 times 10 to the 4. We could have 25 kilopascal, which is 25 times 10 to the 3 Pascal. So be careful of that, right? Read it in the question. Temperature, pressure, okay, and volume, we work in cubic meters, right? I would recommend that you change everything to Kelvin, Pascal, and cubic meters, okay? Technically, you don't have to in this one because it's a direct ratio, but it is safer always to work in Kelvin, Pascal, and cubic meters, right? Because in the next formula that we're going to look at, you have to take it across to those guys, okay? So, obviously, any one of those that we know, we can work it out. Now, let us say that they said to us, okay, let us say they say to us, at constant pressure. Or they don't give us pressure in the question. Essentially what they're saying is that P1 and P2 equals each other. Right? Therefore, leave out P1 and P2. They are the same thing. They will just cancel out. You could just call them 1 if you like. It doesn't matter at all. Not in the slightest. Okay? Similarly, they could say at constant temperature. Or they don't mention temperature at all. They only talk about pressure and volume. It means that T1 equals T2. Therefore, just leave out T1 and T2 in the calc, right? In the calcs. Now, okay, no prizes for guessing, but yes, you're right. At constant volume, what is it? V1 is equal to V2. Therefore, leave out V1 and V2 in your calculations. You don't need it. It's going to cancel out. Okay? Because it's the same number. Okay? You could say, all right, I will call V1 1, and then 1, and that's a 1, it disappears. A 2, it disappears. Right? We just omit it in the calculations. Right? Very straightforward section, this. Okay. Now the last bit we have to talk about with regard to this guy here is going to be standard temperature and pressure. Okay? Now, I'm pretty sure they're given, but let's just look at it. STP. Very important in what we're going to talk about a little bit further on in chemistry. STP, standard temperature and pressure. Standard temperature is going to be 273 degrees Kelvin. Actually 0.15 Kelvin, but I think we omit that. Let's call it 273 degrees Kelvin. That is 0 degrees Celsius. Pressure is 101.3 times 10 to the 3 Pascal, which is the same thing as 101.3 kilopascal. Okay? Please remember those little things like that. Means a big difference between getting it full marks or losing a chunk of marks because we didn't convert that. Okay? So there's our degrees Kelvin. Now, that is standard temperature and pressure. It's a very valuable measuring technique that we're going to be using in the near future. Okay. The last one of these is called Avogadro's law. And what did Avogadro's law state? Okay. Avogadro's law says that at constant temperature and pressure, the volume of a gas will be directly proportional to the number of moles of the gas. Okay. So what did he say? Number of moles, volume, directly proportional, N goes up, volume goes up. That's obvious as well, because the number of moles of the gas, right, is what? It's the number of molecules of the gas, isn't it? And what did we say earlier? We said every molecule that we put in there gives a pressure, doesn't it? And gives a volume. Okay? So if we put one molecule in here, right, into a container, it's only going to occupy its space. The more moles we put in, the more the volume it's going to, the more the volume, right? So that's Avogadro's number. That brings us to the very last part of this section, which is where we put them all together and we get PV equals nRT. Well, pressure in Pascal, volume in cubic meters. N, these guys here, is number of moles. R is a constant. And it's given to you, it's 8.31. The units, I never remember it, joules per degree, Kelvin per mole. Okay? It's not really necessary to remember it. It's given in the schedule with its units. And temperature is temperature in Kelvin. Okay. That relates the pressure, the volume, the temperature, and the number of moles of the gas. Just a little, for those of you who've sort of recognized that if I divide it by T, I get PV over T is equal to nR. Okay? Right? What does this mean? It means that we also know that volume is proportional to N. So I could divide by N as well. That's the same thing as saying PV over Tn is equal to R. That is where the constant R came from. It was the constant of proportionality to make that work. That's where the 8.31 comes from. Okay? But just so that you, for those of you interested, this piece here, remember, that's very close to P1 V1 over T1 is equal to a constant. One universal constant that puts them all together. Well, we know that finally, the last formula that we have to remember is P1 V1 over T1 equals P2 V2 over T2. So the two formulae in this section that are important are those and that one. Well, let me rather highlight it as this. Okay? This one here, PV equals nRT. Okay, and they're given to you in the schedule. You just need to know how to apply them and how to use them. Okay? Essentially, how do we approach problems with the gases, the ideal gas situation, right? We approach them by, I first of all identify, are we changing one state to another state, right? And what are we given? That's the key part. Are we given moles? Are we given this? Are we given that? Let us say, for example, that we've got, let's think about an example. We've got 2 moles of nitrogen, okay? 2 moles of nitrogen, and we say that let's have a look and say, right, the temperature of this is going to be 310 degrees, let's call it Celsius, okay? And the volume is equal to 0.5 cubic meters, okay? I don't know, what's the pressure? Let's have a look. PV equals nRT. Well, what do we know? First of all, we have to convert that to Kelvin, don't we? So we must plus 273 onto that. 310 plus 273, let's have a look. 210 plus 373 is going to be equal to, my bad, 210 plus 273 is going to be equal to 483 Kelvin. Volume is in cubic meters, so PV, all right, let's put in what we know, black. P, no. Volume, 0.5 is equal to N, we've got 2 moles, times 8.31 times 483. So therefore the pressure is going to be 2 times 8.31 times 483, okay, divided by 0.5 is going to be 16.054, or let's say 16055 rounded off Pascal, which is going to be 16.06 kilopascal, right? So there we go, okay. Now the last bit of this is where we say, okay, we are going to have gases at STP, all right, and there's a rule that comes out: 1 mole of any gas at STP occupies 22.4 cubic decimeters, right? That's something that we've got to remember, and I think it's also on the schedules. I'm not 100% sure, but we'll check up on that one. That's the 22.4 cubic decimeters, right? Please remember 1 cubic decimeter is equal to 1 liter, because they're going to give it sometimes in liters, or ask how many liters. Why? Because if you've got a container that you want to fill, okay, you need to know how many liters that container is, right? Because you want to know when it's going to be full, or when the pressure is going to be exceeded. Because if you try and put too much in, the pressure of your container could be exceeded, which means it would go boom, right? So that's the ideal gases scenario. Okay. It really and truly is a very, very easy section of the work. What do? We put everything in cubic meters, into Kelvin, and Pascal, newtons per square meter. Don't get tripped up by 10 to the 6s, megapascal, kilopascals, okay? Put them all like that. We have to remember standard temperature pressure. When we've got everything, we then look at what we're given. Are we changing from state 1 to state 2? PV, P1V1 over T1 equals P2V2 over T2, right? The last bit is to say, hang on, if they give me a constant volume, or don't talk about volume, you just assume the volume stays the same and ignore it. Same for constant temperature, ignore T. Same for constant pressure, ignore P, okay? How could that be so? How could we change something and the pressure stays the same? Simple, you've got a pressure release valve. If you look at if you ever looked at a pressure cooker on a stove, okay, you will see that it's got a, let me see if I can just draw it here. We've got a, like this, right, like so, and we put a lid on it, don't we, with a handle over here like that. I'm not a great artist, I've said before. And on top of it, it's got like a little thing like that. And as the heat at the bottom builds up and builds up and builds up, what's happening? We're giving each individual molecule more energy, right? The temperature's going up. Now, the more energy, the greater the pressure. The pressure increases. This is a pressure cooker. This is how it works. As the pressure gets to the point which is too much and this is going to blow up, this thing here is set on a spring. and it pops up and it releases some of the pressure. It releases those molecules that are moving so fast, right? And then it goes down again because the spring, right, is set that the pressure, the force upwards and the force downwards of the spring, the pressure forces it up is greater than the force downwards, not in equilibrium. Remember, force up bigger than force down, we're going to have a movement, therefore the spring gets pushed up and the pressure can escape. And once the pressures escape, the force up drops and it pushes down and we're back to equilibrium again. Okay? So that's some of the practical uses of it. As I said, you know what, the one with the balloon is really cool. Don't close up anything that's boiling. Don't even try and hold lids down. It is dangerous. It's not something that we do, okay? Because that pressure will build up, and when it flies off, you get something called superheated steam. That kind of is not stuff we want to play with, okay? We're going to move on in the next phase. We're going to start talking about the stoichiometry section. I want to do a little bit more on the stoichiometry, just to make sure that the basis of the stoichiometry is well established. How we calculate, I use a table method, so that's what I'm going to put in. I'm going to do a recipe. This is what you do. You do A, you do B, you do C, you do D, and you get the answers at the end, okay? We're going to do quite a few of those. We're going to talk it through, but we're going to focus mainly on examples in that section of how to calculate it and how to set that table up, because you're going to find that it goes into everything that we do. Next year, this year, the rest of it, and into next year as well. Okay.